Mr. Bergman.
Hey, I'm Mr. Sam.
What are you doing, and who are these people?
Oh, I don't know. Hi guys. Yeah, we're teaching a class on juggling. No, actually about podcasting.
I didn't know you could juggle.
I know. Well, I'm a man of many talents.
I can't.
Do you know why I've got oranges, Mr. Sams?
What? I know. I was going to ask you why in the world do you have oranges.
We're talking about atoms.
Oh, yeah. Obviously, is why you then have oranges.
Well, oranges they're spheres, and atoms are spherical, right?
Ish.
Well, they're kind of like a sphere, aren't they?
Okay, well, kind of.
But the question today is how many atoms fit in an orange?
Oh.
So I think we're going to talk about that and learn about the size of an atom.
Already?
So let's do that.
Sounds good.
Okay.
There you go. I'm pretty good at the juggling.
I know. I think you've got a future in the circus.
Yeah. Well, I learned it while I was a lifeguard.
A lifeguard? You had nothing better to do.
We had nothing better to do while we were being lifeguards. It was in the rain.
What? And where was that?
In Oregon.
Note to self: don't swim in Oregon.
Hey, the point of the orange is, of course, we're going to learn about the atom and how small the atom is. So
yeah. So why oranges and atoms? I don't get it.
Because they're spherical.
Oh.
So you'll see.
Okay.
I think you'll find it as you learn. Okay,
right.
Cool. Hey, before we do that, we need to learn about the history of the atom.
History lessons in science.
Why would you learn history? I thought it was just like in history
we got to
class.
know how we know what we know.
I agree.
How we got there.
Yeah, that's important. So we're going to start with this guy right here. His name is John Dalton.
John Dalton, British scientist.
Yeah.
Came up with something called Dalton's atomic theory.
And he had kind of 4 parts to his theory.
Yeah, there was kind of this big gap. There was an ancient Greek, Democritus, I believe was his name, and he came up with the idea of the atom, and then Aristotle went, and everybody liked Aristotle better, and so they kind of went with what Aristotle thought about the existence of tiny matter, and so the idea of the atom kind of got squished for a couple thousand years, and then Dalton kind of resurrected it back in the 1800s.
Johnny came back about 1850, I think it was, and he said, you know what, atoms are small.
Yeah.
Notice they are tiny particles.
Yep.
And he said elements.
Yeah. So
we talked about elements.
Smallest bit of an element, he would say, would be an atom, and that's the smallest particle.
So he kind of envisioned atoms as tiny spheres.
Yeah.
Some are bigger than others. Maybe this is the hydrogen atom, and then a larger one might be, a sodium atom. Okay.
S. Not S.
Okay. The second thing he said is that they are all identical.
Right. So all
of the same element.
Right. All copper atoms would be the same as all other copper atoms.
And it turns out he was actually wrong about that. That is not exactly true.
That's true. And he was actually wrong about the first one, too. He said they were tiny and indivisible.
Yes, and we've actually figured out that they contain parts.
Yeah.
We'll get to there. And atoms of each element were different from one another.
They are.
Was correct
and that
about
was true.
That.
Yep. So a copper atom is different than a sodium atom, which is different than a neon atom, and so on.
Yep. So you kind of get the idea. And he says that they can make compounds.
Yep.
And we talk about compounds in Unit 1. Compounds, of course, we have 2 or more elements combined. So, for example, CH4 is methane gas, and that's where the carbon combines with the hydrogen. But, of course, they're spherical, so he'd kind of envision it something like that.
Yeah.
Okay.
All
right. So that's kind of his deal. But what we do know at the atom is that they are...
Small.
How small are atoms, Mr. Sands?
Very small.
Well, let me help you by looking at an orange.
Okay.
So, Mr. Sams, you remember the orange?
I remember the oranges.
Yeah, so the orange. How many atoms are in an orange?
At least 5.
I think you're probably right about that, but I think it's a lot more than 5.
10.
You see, there's a lot of atoms in the orange. In order to kind of envision this, you have to take the orange and you have to blow up to the size of the Earth.
Okay.
So, like, think of an Earth. And now the atoms
and
are...
Earth?
And Earth. The Earth.
Okay.
Atoms would then be the size of cherries.
Wow. That's a lot of atoms.
So envision the orange blown up to the size of the world, and the atoms are cherries. That's how many atoms are in the orange. Wow.
All right, so there's my Earth-sized orange right there, and the whole thing is filled with actual sized cherries. That is a ton. That's so many stinking cherries. I can't even really get my head around how many that is.
It is so unbelievable. So you take the orange, you blow it up to the size of the world.
Yep. And then you
cherries.
Fill it with cherries.
The Earth filled with cherries. Wow. Right. That's amazing.
That's all right, so I'm going to take those cherries and I'm going to fill up the Earth with the cherries.
Yeah.
Wow, that's big. Big funnel.
That's a big funnel, yeah. Well, the idea was the cherries kind of go through the funnel and fill the Earth. Yeah.
So that's just gazillions of cherries.
Unbelievable, isn't it? Yeah.
So and there's that many That's crazy. That many atoms in an orange.
I know.
Wow.
It's crazy. But that's the way it is.
They're tiny.
Yeah,
Okay.
They're tiny.
I believe you.
Hey, as we go a little further in history, we meet a guy named J.J. Thomson. Yeah, J.J. Early 1900s. Yes. And he did a really cool experiment. And so why don't we watch that experiment right now?
Okay.
Okay. Mr. Sams, that was pretty cool.
Yeah.
Boy, you can actually bend light with a magnet.
Yeah. You put the magnet up there and it bends that beam of electrons.
So what had he discovered?
He discovered that there were electrons,
Yeah.
negatively charged particles. So that what that did is it took Dalton's theory of atoms as being the smallest particle and said, well, there's something smaller than the atom. There's something in that atom that's negatively charged.
So here's a picture. So guys, as you're watching this, make sure that you're copying down the pictures of the atoms.
Yeah.
You may need to pause the video as you do that.
Yep.
But here's he called his model the
plum pudding model. But since we live in America, we don't know what plum pudding is.
Yeah.
So I like to call this the chocolate chip cookie dough model.
I agree. Chocolate chip cookie dough.
Yeah.
So it's spherical spherical chocolate chip cookies. And the chocolate chips, of course, have a negative charge.
Those are the negatively charged chocolate chips and a positively charged cookie dough.
Yep, the cookie dough has a positive charge.
The whole thing itself has a positive charge. Yeah,
Mm-hmm.
that was his model. He said there are these negatively charged things living in this kind of cloud of positiveness.
And of course, as we added the energy to that cathode ray tube, what was shooting out were the electrons.
The electrons, right.
And then they were attracted to the magnet, as we saw.
Yeah.
Okay. And then we get to another guy, Ernst Rutherford.
Yeah.
He was 1915, I want to say, roughly. And he also did a very cool experiment. What did he do, Mr. Sam?
He did the gold foil experiment. So what he did is he took this radioactive source and he fired what are called alpha particles through the piece of gold foil. And those alpha particles, it's essentially a helium nucleus. It has 2 protons and 2 electrons. So it has a decent amount of mass in it. And he fired them through this piece of gold foil and he said, all right, if Thomson is right, then all my all my alpha particles are going to go flying right through the gold foil. They're just going to go straight through because Thomson said it's mostly empty space.
Yeah. Mm-hmm.
But what happened is some of these things got bent. They didn't all go straight through. They kind of got deflected a little bit, and some of them bounced completely off. And he said, whoa, that's interesting.
You know what his quote was? He says, it was as if I shot a cannonball at a piece of tissue paper, and it came back at me.
Yes.
He was very shocked.
Yeah.
And then he said at the atom, he says, this tells me something amazing about the atom.
He said there has to be something very dense and positively charged in that atom somewhere that these alpha particles are bouncing off.
So what did he discover?
He discovered the nucleus. Yeah. He said instead of having a cloud of positive cookie dough, if you will, all the positive charge is compressed in the middle of the atom.
That's right.
And it bounced off.
Now this picture shows us kind of how big that nucleus would be, right?
Well, no, that's not a real good representation of the size of the nucleus.
So the nucleus is kind of small.
It's really small.
Yeah.
Yeah.
Actually, let's illustrate this with a little clip. What do you
let's
think?
go out to the football field.
Yeah, let's go to a football field here at Woodland Park and see if that can help us understand it.
Okay.
So we've already talked about how big or really how small the atoms are. Atoms, of course, are really small. It's the number of atoms in the orange is equal to the number of cherries in the earth. But now we want to look at the cherries. So I don't have any cherries, but I have a ping pong ball. So let's say the ping pong ball, it's a little bigger than a cherry, but pretend this is now, how big is the nucleus inside of the atom? And of course the nucleus would be like the core, the center. It would be the pit of a cherry, right? But how big is that pit? That's what we want to look at. And so to illustrate that, we're here at the Woodland Park football stadium. And so what we really want to do is to say, how big is that? Okay. Now I've also brought with me one other thing. It's a tiny little bean. Okay. So this would be like the size of the pit that you would put inside of the cherry. Is this the right size? So would this be appropriately sized for the nucleus? Well, the answer is no. We're going to actually have to blow the nucleus up, or probably the atom up, to the size
of the football stadium. If you blow up the ball to the size of the football stadium, it's unbelievable.
So Mr. Bergman is down there on the 50-yard line. He's got his little bean, and that bean is the nucleus of the atom. And the whole radius of the atom is about the size of this football stadium. That's huge, and the nucleus is really tiny. The crazy thing is almost all of the mass of the atom is in that nucleus, is in that bean. So think about the most dense bean in the world you could possibly imagine. We're talking like tear your arm off dense. It's so heavy for such a small size.
Wow.
Yeah.
It's small.
It's tiny.
That bean was small.
But it's extraordinarily dense. If you were holding it, it would tear your arm off.
Yes. So in fact, you know how dense it is?
How dense is it?
How dense is the nucleus? Well, if you took a cubic centimeter, all right, everybody take your index finger and then find your fingernail.
Okay.
Okay. Your fingernail is about 1 centimeter in width.
All right, so 3-dimensional size of my fingernail.
So if you have a box 1 centimeter by 1 centimeter by 1 centimeter,
made out of nuclear material,
made out of nuclear material, it would weigh 2,000 tons.
2,000 tons?
That's correct.
Holy cow!
So go out.
How do you know this stuff?
Because I'm amazing. Go take your average small car, like a Honda Accord or something like that, out in the parking lot.
All right.
That weighs about 1 ton.
Okay, so 2,000 Hondas,
2,000
the size
Hondas,
of my fingernail.
The size of your fingernail.
Wow.
That's dense.
That's very dense.
Really, really dense.
That's pretty cool.
That's pretty cool, yeah. Okay, and then we meet our last guy.
All right.
Niels Bohr.
Niels Bohr.
He was from Germany, and he talked probably German stuff, I think.
Is that a German accent?
I don't think so. I don't know.
I don't know what that was.
I don't either. So Niels Bohr, what did he say?
Well, he said that the electrons are
okay,
moving around the nucleus like a planet orbits around the sun.
Yes, orbits.
Yes.
I see. Okay.
Right.
That's it?
Yeah, they're moving in a nice little line, and they occur in particular energy levels.
Yeah, he called them shells.
Yes, energy shells.
So he had energy shells, and the electrons, they moved in particular shells, right?
You're fading into Russian now, I think.
Is that Russian? I thought it was German.
I don't know what that is.
I don't either. I tried to be German. I don't know. Okay,
No.
so he had the shell model, right? Okay, so what's the summary? All right, let's just take a look. We've got several guys. Dalton.
Right, Dalton.
Basically, Dalton. So, folks, you should write this down. Just kind of just a real quick picture. Dalton believed in tiny spheres. He didn't know what was inside the spheres.
No, he thought that was the smallest particle he could get.
Thomson said, "Yeah, they're spheres," so he agreed. Except
they have electrons in them.
They've got electrons, and there's this. It's the cookie dough guy. Right.
Plum pudding, cookie dough.
Yeah. And then we meet Rutherford. And he said, Thomson, yeah, there's parts of the nucleus, or there's this nucleus, but it's so tiny.
Tiny, dense, and positively charged.
Yeah, and the electrons are somewhere on the outside. He didn't know this story.
They're outside
and
somewhere.
lastly, and there's still another guy, but we'll deal with him later.
Yep.
And that's Bohr. And Bohr said, yep, got tiny, super duper tiny nucleus. Now the electrons are traveling like planets around the sun.
And they do that in particular energy shells.
Specific energy levels.
And he was wrong.
And he was actually wrong.
But that's okay. We'll talk about that in Unit 8. Yeah,
we're not going to get to it. The present-day model is actually called the quantum mechanical model. And we'll get to that later. You need some more science.
And it's built off of what Bohr did. I shouldn't say he was wrong. He just was incomplete.
Yeah, that's probably good. Yeah. So really, it's not like any of these guys was wrong. It just progressed.
That's just what they knew at the time.
As time went on. And that's what we know.
Exactly.
So that is the history of the atom.
There it is. I think I'm going to go eat an orange.
Yeah, I'm pretty hungry. I think we should do oranges.
All right.
All right.
Sounds good.
All
Bye, guys.
Bye.